Okay, so well, good morning from good morning to people in Montreal, and good afternoon to people from this side of the of the world. So as George said, I'm Julia de Frutos. I'm assistant professor at the University of Barcelona in the Department of Mathematical Economics. Also, I'm part of the BIRT, that is the Barcelona Economic Analysis team. So first of all, I would like to thank George and indeed the rest of the organizing committee of these webinars for because of the invitation. It's always a pleasure. I will present today this work, as George says, a Stackelberg competition in groundwater resources with multiple uses. This is shared with paper shared with Guiomar Martinez-Ran from the University of Valladolid and Mabel Tidbal from the Center for Environmental Economics in Montpellier. So this is a paper that I have already presented at the ISGG conference in Porto. Then I'm sorry for colleagues that they have already listened this presentation, but I think it's a nice occasion to present the longer format and to have more detailed comments and to have more details about the paper in order to improve it. So please stop me when you want during the presentation. Then to put in context our work, the fifth assessment report of IPCC, that is already the previous IPCC report, already advised that climate change is projected to reduce renewable water resources significantly in most subtropical regions. And this will exacerbate competition for the different uses, that is agriculture, ecosystem, settlements, industry, energy production, affecting regional water, energy, and food security. Indeed, groundwater depletion is a challenge, and more in this context in which groundwater resources are playing an increasing important role, not just for the uses that we know, irrigation, drinking water, but also for new uses, as for example, indeed, energy production. So in this context, we address today a specific problem. We address a problem of exploitation of a groundwater resource that is mainly used for irrigation. So the regular use of this resource is these are farmers, the users, but they should face the entrance of an exceptional and priority use in the system. So to put in context this with an example, so we have a resource, farmers are just the only users of this resource, and suddenly there is a special need for drinking water, imagine, because of water scarcity in a urban area. So we depart from the assumption that in this case, so a benevolent water authority, for example, a water agency that exceptionally prioritize this new use over the regular use, could be better to solve the water conflict than a regulator that is in charge of implementing efficient policies during a longer period of time. For this reason, we will step away from the literature of centralized management, and we will introduce the strategic aspect in the modeling. In fact, the use of dynamic games, that is the strategic and dynamic interaction between the different agents, has been largely justified in the literature. So using game theory and addressing this type of problems of common pool resource problems in general, so most of the papers focus on analyzing and comparing different type of non-cooperative Nash equilibria with the socially optimal or cooperative solution. However, when water conflict enters the problem, Stackelberg games, or in other words, leader-follower approaches, can offer a more real representation of the practical problem, can be more realistic. We know that the difference between a Nash and a Stackelberg is that in a Nash, players decide simultaneously, and in a Stackelberg game, the leader chooses first, and the follower decides subsequently, depending on the actions of the leader. We also know that different types of Stackelberg equilibria exist, depending on the type of commitment between the agents and or information available to decision makers. In this paper, we will consider two players, two agents, a leader, that is the water agency, and a follower, that is a representative agent of the farmers, the regular users of the resource. We will study two types of Stackelberg equilibrium: Stackelberg open loop equilibrium and Stackelberg feedback equilibrium. So which is more realistic? Well, as we know, it depends on the information available and also on the type of commitment between the agents over the different periods of the game. On one hand, when the state of the resource can be observed at each moment, we say that Stackelberg feedback strategy are more appropriate. However, when the state of the resource can be observed with a delay or cannot be observed, Stackelberg open loop strategies are more realistic. On the other hand, with respect to the type of commitment and time-consistent solutions, the structure is different. So in the open loop case, the leader commit about extraction behavior over time, and then the follower believes this commitment and takes decision under this belief. So in most of the cases, papers show that this type of solution is not consistent over time. Why is not consistent? Because the leader could deviate in a moment from the initial strategy. Why it could deviate? Because maybe at this moment, the problem of the leader, taking into account the optimal extraction decision of the leader or the optimal plan of the leader at this moment, taking into account past decision, is not the same. It's not the same solution. It's not the same than the optimal plan that was planned at the beginning in the commitment solution. In the feedback case, this does not happen. Sorry. The leader and the follower do not commit about their optimal plan, about the plan of extraction, sorry, and they decide at each stage depending on the state of the resource. So this type of equilibrium is time consistent. So the analysis of both topics, so competition between groundwater uses and the comparison between different types of Stackelberg equilibria, motivates our research question today. We want to answer to this question: which type of extraction strategies, Stackelberg strategies with or without commitment, in other words, Stackelberg open loop or Stackelberg feedback strategies, which type of extraction strategy is more profitable for the sustainability of the resource and or for the agent's profit. When we say sustainability of the resource, we say in terms of the final resource stocks. And when we say agent's profit, we say for the leader, the water agency, and for the follower, for the main, for the representative of the main agent that represents all the farmers. So to answer to this question, we look as always to the literature of exploitation of groundwater resources. Sorry. As I said previously, most of the literature focus on analyzing different type of non-cooperative Nash equilibria with a socially optimal solution for irrigation users, because it's true that is the main or the regular use in most of the aquifer. In general, for symmetric players, we have here Santiago Rubio. So we take always these papers are reference, Rubio and Casino 2001. We have papers also that takes into account symmetric players, but also other characteristics as water scarcity, water quality, environmental damage, as Esteban and Albiac 2011. But it's true that a few papers consider asymmetric players. There are papers indeed, but a few papers consider asymmetric players, and even less, especially multiple uses of the groundwater resource. So in this paper that we published in 2021 with Jesus Marin from my department, that you know, and also Jorge Navas. We address this type of, well, we address also a problem of competition between different groundwater uses, but here we focus on comparing different type of subgame-perfect, non-cooperative and cooperative solution. The problem here is that the practical problem that we want to solve is different. So for this, we need, as I explained previously, a Stackelberg or leader-follower approaches offer a more real representation in practice. So looking to the literature of Stackelberg games in resource problems or in groundwater resources, we have some theoretical studies that offer interesting results from a theoretical perspective, but few papers, again, compare, to the best of our knowledge, in any case, few papers compare different type of Stackelberg equilibria. This is the case of NIE, for example, 2005. With respect to empirical studies, they try to find algorithms to find approximate solution to really complex problems. The problem is true that is similar, a water quantity management problem under competition between different uses. And an example is Kixini et al. 2014. That is the paper that is more similar to our paper with respect to the topic. What is the difference of our paper with respect to these two papers and in general with respect to the literature to the best of our knowledge? In our paper, the leader just intervenes when it's necessary. That is when the new use takes place. In these papers, in these Stackelberg papers, there is a leader-follower approach at each stage of the game. Next, in our paper, we consider a benevolent, we call it a benevolent water authority. This can be a water agency, because this water authority consider in her objective the profits of the different uses of the resource, and also because she can allocate different weights to the different uses in her objective function. That is one of the contributions of our paper today. Finally, as I said previously, a few papers compare different type of Stackelberg equilibria. This is the case in Kixini et al. 2014, just the feedback strategies analyzed. They try to find with an algorithm an approximation of this feedback solution. In our paper, we compare open loop commitment strategy and feedback non-commitment strategies. So I hope that until here is clear. If you have any question. So before presenting the rest of the work, let's summarize important findings in the literature, also to see what is the contribution of the paper in theoretical and empirical terms. In the previous literature of Nash equilibria, I will say now why I'm talking all the time about Nash equilibria if I'm presenting an Stackelberg game. So in the previous literature of Nash equilibria, generally non-commitment feedback strategy, or in any case in the literature that I have mentioned previously, okay, groundwater resources, non-commitment feedback strategy do not provide higher stock levels than pre-commitment open loop strategy. And also, feedback strategy do not provide higher user profits than pre-commitment open loop strategies. Unlike this literature, in the case of Stackelberg equilibria, in particular, NIE 2005 shows that non-commitment feedback strategy provides higher leaders profit than commitment open loop strategy. That is that for the leader is not worth to commit. Okay, it's taking the decision first, and it's not worth for the leader to commit. So our case is slightly different because, well, we call it a degenerated Stackelberg equilibria. We don't know if this is a good definition, but it's true that as the leader just intervenes when the new use takes place, is not a real leader-follower approach at each stage of the game. So we will see that in some situation, we will be closer to the Nash result. It's for this that I'm talking about Nash all the time. And in other situations, we will be more close to the Stackelberg results. Anyway, unlike the literature of Nash equilibria, we will show that in some situation, non-commitment feedback strategy could provide higher stock levels than commitment open loop strategy. And also, we will see that commitment strategy feedback, non-commitment feedback strategy could provide higher user profit, not just for the leader, but also for the follower. In this case, than commitment open loop strategies. Let's go then to the definition of the game. We need to model, or we want to model a specific problem. It's true that it's not the typical Stackelberg game. We want to model a specific situation, which is the need of a special need of a benevolent water authority, for example, a water agency, in order to manage this exceptional extraction of water for a non-agricultural use that can be, for example, domestic water in case of water scarcity. To solve this problem, we build a two-stage discrete Stackelberg game with two players. A representative agents for agricultural users, that will be the follower of the game, and a water agency that will be the leader of the game. So the problem consists the leader announces at t equal to 0 that there will be an exceptional extraction that we call G12 for a new use at the beginning of the second period. So this problem has several control variables. We have the extraction rate of the follower in period 1 and period 2. This is the extraction rate of the regular users of the resource, the farmers. And G12, that is the extraction rate of the leader for the new use in period 2. And we have, sorry, we have one state variable that is the stock of water at time t, capital G T. So at the end of the first period, the stock of water is equal to the initial stock minus extraction of the follower in the first period plus a constant recharge rate. At the end of the second period, the stock of water is equal to the stock of water at the end of the first period minus extraction of the follower in the second period minus extraction of the leader for the new use in the second period plus a constant recharge rate. As we can see here, there is just competition between the different uses in the second stage or the second stage of the game. In the first step, just the regular users, the farmers, are extracting. The follower and the leader aims to maximize profits from groundwater use. In particular, the follower objective is to maximize profit from the main activity over the two periods, that is from agricultural activity over the two periods. We assume that the per period profit of the follower is net revenues minus pumping cost here, as usual in the literature. We assume also the revenue function is here linear with respect to extraction. This can be seen as a limitation, and indeed in most of the literature, they consider a non-linear revenue function. So what we will do, we should be honest, we make this assumption because in order to have some analytical result, but what we will do is to make a numerical simulation in the numerical part to the case of non-linear revenue to see if the result that we will find now for this case are maintained for the case of nonlinear agricultural revenue. Pumping cost, as usual, depend on the stock of the aquifer and on extraction. Unit cost or marginal cost are linear with respect to the states, as always, and indeed unit cost are lower the higher the stock of the resource. With respect to the leader objective, she aims to maximize a weighted sum of the profits for agriculture and the profits derived from extraction for the new use in the second period. The per period profit of the follower is defined as exactly as previously, indeed, and the profit from the new use in the second period, as we can see here, is defined qualitatively similar to the one of the follower, so linear revenue, quadratic pumping cost that depend on the stock and the extraction. However, the parameters of the revenue function indeed are agent specific in order to distinguish the different type of uses. Let's go to solve then our model. So we should solve the Stackelberg game. The leader chooses first and the follower decides subsequently depending on the action of the leader. And we know that different type of Stackelberg equilibria exist depending on the type of commitment between the two agents over the different periods. The main idea in an open-loop equilibrium, we say that the leader commits about extraction behavior over time, and then the follower they decide subsequently under this belief. Our Stackelberg is a bit different. So the main idea of our problem, that is not a leader-follower approach at each state, is that the leader commits about his extraction in the second period, G12, because it's not extracting in the first period. And then the follower believes this commitment and chooses his path of extraction over the two periods, G1F and G2F. So the first step is the follower's problem, should find extraction that maximize the sum of profits over the two periods. He is writing 1 and 2, it's not very pretty. It's taking into account the dynamics of the resource. This is the dynamics of the resource and positivity condition of the states at the end of each period. We will then obtain the follower's reaction function in each period that depends on extraction decision of the leader in the second period. We insert this function in the leader's problem. So what is the leader problem? The problem is that to find an extraction for the new use that maximize now a weight sum of profits of the follower and the new use, agriculture and the new use. Here theta is the weight assigned to the follower profits, theta is between 0 and 1, and 1 minus theta, the weight assigned to the new use profits, taking into account the dynamics and positivity condition of the states. In the feedback equilibria, now the leader and the follower do not commit and take decision at each moment depending on the state of the resource. But in our case here, the problem, as the leader is not extracting, the problem starts by, we can do it in 3 steps. First, the follower chooses in the first step his strategy, G1F. Then the leader announces his strategy in the second period, G12. And then the follower believes this announcement and chooses his strategy in the second period, G12. To solve this problem, we should do it then now in 3 steps by backward induction. First, we solve the second period follower problem, find the extraction that maximize profit just in the second period, but taking into account the dynamics and positivity condition. We will obtain now a follower reaction function in the second period that depends on the extraction of the leader in the second period, but also on his own extraction behavior in the first period. We insert this reaction function in the second stage of the game, the leader problem. In the second period, he should find now G12 again that maximize a weight sum of profits, taking into account the dynamics. We obtain the leader reaction function now that is just depending on the extraction of the follower in the first period. We insert these 2 functions in the first period follower problem, that is also dynamic, and we solve it. So what we will do in what follows, we will first derive analytical result of the previous problem for the 2 types of equilibria. We then will present solution and compare theoretical results for the benchmark case under the 2 equilibria, theta equal to 1/2. So theta equal to 1/2 is the casing with the leader equally values both uses in the objective function. And then we will carry out numerical simulation for other economic assumptions. First of all, we have an analytical result in the open loop case. So we will work with this optimal solution. And the first thing is to study sufficient conditions for optimization, for concavity, and also positivity condition. With respect to concavity, we have a solution when theta is lower than 2/3. In other words, the weight assigned to the agricultural profits, that's the main users of the result, in the leader's objective should not be very high. So, sorry, should not be close to too close to 1. In this case, it's not worth to introduce a new use in the system. With respect to positivity condition, we are interested in a strictly positive condition. Indeed, we assume that the farmers need water for irrigation. And also, we assume that the extraction of the leader for the new use should be positive, because if it's 0, there is no problem to solve. There is no competition between different uses. So we derive all these conditions that can be summarized in these ideas. So the new use or activity that enters in the game needs to be more profitable than the main use of the aquifer. And the level of the resource at the beginning of the planning horizon must be high enough to procure these activities. We now perform a sensitivity analysis with respect to theta. That is one of the main parameters of the model, the weight assigned by the leader to the agricultural profits. Very quickly, we show that when theta increases, that is when the agricultural profits are more and more important for the leader. This is positive, indeed for them, for the follower, for the extractions, also for the resource, for the profits of the follower, indeed, and for the resource, but it's negative for the leader, not for the leader, for the new use. Well, we do exactly the same with feedback strategy. We can see here that the expressions are longer, are difficult to treat, more difficult to treat in any case. So it's logical that sufficient condition now will request a stronger condition that in the open loop case. At the end, the interpretation is similar. For concavity, theta, a stronger condition, theta should be lower than 3 divided by 5. The mean is exactly the same. And with respect to positivity condition, we have two options, or we should impose or 4.1 or 4.2. What means 4.1 and 4.2? We should impose, or we must impose, a greater initial stock to procure these activities, in general, a stronger condition, or to avoid lower values of theta, so values of theta that are close to 0. So we cannot have in this case, we cannot have thetas that are too high and too low. Indeed, when theta is too low, extraction of the follower tends to 0, or even can be to negative values. So we are not interested in this case. We perform also a sensitivity analysis with respect to theta for the Stackelberg solution. And we see that main tendencies are maintained. So when theta increases, this is positive for the follower, for the extractions of the follower, the profit of the follower, and also for the state of the resource, but it's negative in terms of the extraction of the leader for the new use. So what we do now is mainly to compare both structures. And we compare it for the benchmark case, the case in which theta is equal to 1/2, the case in which the leader equally values both uses in the objective function, although some results are also valid for the case theta lower than 1/2. So when the leader values less the agricultural profits than the new use profits. We show that first in proposition 3, with respect to individual extraction, we show that extraction of the follower in the first period in the feedback case are higher than in the open loop case, the same for the leader in the second period, and the opposite is obtained for the extraction of the follower in the second period. So the intuition behind this result is slightly different because the leader is just extracting for the new use in in the second period. Then when he or she has extra information about stock levels in the feedback case, the extraction behavior is more aggressive, so extraction are higher. However, for the follower that is extracting in both periods, so what it's doing is that because of competition between uses in the second period, because of this fear of water shortage, in case that that has extra information about stock levels in the feedback case, is anticipating extraction losses of the second period by increasing extraction in the first period in the feedback with respect to the open loop case. This leads to total extraction that are higher in the feedback than in the open loop case, or in other words, to stock levels that are lower in the feedback than in the open loop case. And this result is in line with the literature of Nash equilibria. For the stream cases, theta equal to 1/2 and theta equal to 0, we can also show that this is true in terms of the profit of the follower and the profit of the leader. So profits of the open loop in the open loop case are higher than in the feedback case. So what we do now is to make a numerical simulation to see if these results are maintained for other economic assumptions. For example, for the case of nonlinear agricultural revenue, for the case in which theta is higher than 1/2, and for other economic assumptions that I will explain later. For this, we take parameter values that are consistent or that verify our sufficient conditions, and that they are realistic with this sufficient condition. We first confirm our benchmark case that we have already shown theoretically. So commitment strategy are better for the sustainability of the resource than non-commitment strategy, and they are also more profitable for the resource than non-commitment strategy. Stock levels are higher and profits are higher in the open loop than in the feedback case. But this we have already shown it for the benchmark case theoretically. We now see, indeed, one of the limitations of the model was to take into account this linear revenue for the farmers. So we make simulation for the case of nonlinear revenues from agricultural use. We made a lot of simulation and we create a summary table. I hope that it can be understood. We can see here the sign of the difference between the extraction results in the feedback and in the open loop case. Plus means that the extraction is higher in the feedback than in the open loop case, and minus that the extraction is lower in the feedback than in the open loop case. So we make a simulation for different BF, for different thetas, by period for each agents, and total extraction here in these columns that we can see. To see the influence of taking into account these nonlinear revenues, we do it through the parameter BF. So when BF is higher than 0, we consider nonlinear revenues from agricultural use. We focus on the first line in red, and we compare the different columns to see the influence of an increase in BF. We can compare, for example, total extraction. In this case, we see that main tendencies are maintained. Extraction in the feedback are higher than total extraction in the feedback case. Over the 2 periods are higher in the feedback than in the open loop case. We make the same type of table for the profits. Again, we have the sign of the difference here between the profit result in the feedback than in the open loop case. We can see here the profit of the follower in the first and the second period, the total profit of the follower, the total profit of the leader. Remind that the leader is not extracting in the first period. For different BF and for different thetas. Again, if we want to see the influence of BF, we focus here on the cells in green, and we see that again that it seems that main results are maintained. So total extraction in the open loop, so total profit, sorry, of the leader and the follower are higher in the open loop than in the feedback case. So in summary, what I explained previously, numerical results suggest that commitment strategy are better for the sustainability of the resource and for the resource user for the profits of the resource users when non-linear agricultural revenues are taken into account. Now, next, we make simulations for different weights. For the case of theta higher than 1/2, that is when the leader assigns different weights to the agricultural and the new use profits. We make the same type of table than previously, and now to compare the different thetas, we see here on the left the different thetas. This is the benchmark case, and this is a summary because we did a lot of simulation. We take just 2 values here. We should focus on the lines in red, and we compare, for example, the cells in red if we want to compare total extraction. And in the benchmark curve, we have seen already that total extraction are higher in the feedback than in the open loop case. When theta increases, that is when the leader values more and more the agricultural profits in the objective, so total, we see here a change of sign. So this is one of our main results. So total extraction becomes now lower in the feedback than in the open loop case. And this does not seem that it's because of the extraction of the leader, because the main tendencies are maintained. We can see it here if we compare these 2 cells, but this is because of the extraction of the follower over the two periods. So in the benchmark case, we have seen already that the follower is anticipating extraction losses in the second period by increasing extraction in the feedback with respect to the open loop case. So when theta increased, the intuition behind the result is that when theta increased, that is when the leader values more and more the agricultural profits and less the new use profits. This fear for water shortage, this anticipation decreases, and then total extraction in the first period becomes higher in the open loop case, in the commitment case, leading to total extraction over the 2 periods that are higher in the open loop than in the feedback case. With respect to the profits, again, we should look to this line, and it seems that the profits per period change, the tendencies change when theta increases, but not the total profit tendency of the follower and the leader over the 2 periods. So it seems that results concerning profits are maintained. In summary, when for a high value of theta, non-commitment strategy could be better for the sustainability of the results than commitment strategy, and this is not true in terms of profits. Finally, it's true that as the 2-period model, and it can be seen as a limitation of the study in a lot of, well, if we want to analyze the sustainability of the resource. So in this part, we introduce, in the numerical part, we introduce the possibility that the leader values the final stock levels in the objective function as an scrap value that is capital A times the final stock of the resource, if I remember well. So the case in which A is higher than 0 is the case in which the leader values the final stock levels, and the case A equal to 0 is the case in which the leader does not value the final stock levels in the objective. So we make the same type of tables here to compare, to see the influence of taking into account this valuation of the final stock levels. We focus on these 2 lines. So it seems that results are maintained when A is equal to 0 and when A is higher than 0 for the extractions and for the profits. But as I said, we did a lot of simulation, so we observe an interesting result for a high value of theta here. So here we can see extractions on the left is another type of table, but the main the meaning of the sign is exactly the same. Plus means feedback higher than open loop, and minus means feedback lower than open loop. This for extractions, and on the right for profits. And we see that main tendencies are maintained when we consider this valuation of the stock levels. Sorry. A ver, que me he ido. But not in the case of the total follower profits. And the total profits of the follower are higher in the open loop than in the feedback case, but this changes when for this situation. So the intuition behind this result is that when the evaluation of the final stock level is considered, the leader will extract in the objective of the leader will extract less for the new use, less competition for the different uses, less strategic and dynamic interactions in the feedback case. So the follower will profit of this to extract more and to accumulate profits in the second period, leading to profit that at the end in total are higher in the feedback than in the open loop case. In summary, when the valuation of the final stock levels is considered, non-commitment strategy could be better for the sustainability of the resource for a high value of theta. So stock levels can become higher in the feedback than in the open loop case. And also, this can be better for the profits of the follower. We will see now that we did not observe this for the leader. So, in conclusions, or as conclusions, first, analytical results. So analytical results show that when the leader assigns a lower or equal weight to the profits from the agricultural use than to the profits from the new use, we have seen that commitment strategy provide higher stock levels than non-commitment strategy. This result then goes in line with this literature of Nash Equilibra, Negri, Rubian Casino, the Frutos, some papers that we have done previously on the same topic, not just for the case of symmetric players, as is the case here and here, but also for the case of asymmetric players. For the case of equal weights of both uses in the objective of the leader, we show that this is also true in terms of profit. So commitment strategy provide higher user profits than non-commitment strategy, also in line with these two papers that we have done previously, in which at the end we compare games in which players decide simultaneously. With respect to numerical results, they suggest that when the leader assigns a higher weight now to the profits from agricultural use than to the profits from the new use, commitment strategy could not provide higher stock levels than non-commitment strategy. So non-commitment strategy could be better for the sustainability of the resource than commitment strategy. Result that does not go in line with indeed with the literature that we have said previously. And when the sustainability of the resource is considered in the leader objective, numerical results show that when the leader assigns a higher weight to the profits from agricultural use than to the profits from the new use, commitment strategy could be non-commitment strategy. Sorry, could be also better for the user's profit. In this case, just the follower profits. That is a result that is not also found in the literature of Nash Equilibra. Anyway, as I said previously, in any case, numerical in all the numerical simulation, we show that that the leader will always prefer to commit, so that commitment strategy always provide higher profits for the leader than non-commitment strategy. This result does not go in line with the literature of Stackelberg game. We see that in Stackelberg games, in this case in year 2005, they show that the leader will always prefer to not commit. So in this sense, results are more closer to the literature of Nash Equilibra. But it's true that this is not a proper Stackelberg game, in the sense that we call it a degenerated Stackelberg game, in the sense that the leader is not extracting in the first period. Moreover, we have shown in the numerical result that in some situations, non-commitment strategy could provide higher profits for the follower than commitment strategy. So this is an important result. It's true that this is just in some numerical in some situations, but the follower at the end is the only that is extracting in the first period. So even if it's the leader that decides to commit to not commit, as the follower is deciding, it's just extracting in the, is the only that is extracting in the first period. If there are some situation in which she can have more profits in the non-commitment case, the follower could deviate from the decision of the leader, place non-commitment, and then force the leader to play non-commitment also in the second step. As possible extensions, indeed we can consider multiple players, multiple followers playing a LANASH instead of a representative agent for the farmers, and that they also play a Stackelberg with the water agency as a leader. We can also check the efficient optimal solution to compute the efficient optimal solution in order to derive a possible policy implication of our study. And finally, we could try to apply this to a real case of a study, because sometimes you apply to a real case of a study and at the end there is no real difference with values. There is no real difference between the two type of equilibrium. So thanks for your attention.